we're going to explore further looking at radicals and simplifying them. In this lesson, we're going to look at radicals in the denominator and then also some special advanced cases for when you have an even index and you're trying to simplify a radical. So first of all, let's talk about fractions. If you have a binomial in the denominator that involves a radical, like one of these two, and here we're only going to look at square roots. We're not going to look at other indices like a cube root or a fourth root. But when you have a binomial in the denominator, you're going to multiply the top and bottom by the conjugate. Now, just a reminder, you might find that familiar because you probably have done this process in Algebra 1, and then also earlier when we were looking at complex numbers, when we had an I in the denominator, a complex number that had an imaginary part, we also multiplied by the conjugate. So it should be a very familiar idea. And just so you know, when you have a plus the square root of b, the conjugate is a minus the square root of b, and vice versa. What you do is you don't change the sign on the first number, but the operation in the middle, if it's a plus, make it a minus, if it's a minus, make it a plus, multiply by it in the numerator and the denominator. Now, if you just have a monomial in the denominator, you want to create a perfect square or a perfect cube or a perfect whatever the index is. So you want to create a perfect square or cube or whatever the index is. All right, so let's go ahead and look at a couple examples here. The first one is we have 1 minus the square root of 5 in the denominator. So we're going to multiply by its conjugate, which is 1 plus the square root of 5. And we're going to do it in the top and the bottom. The reason why we do it in the top and the bottom is because when you multiply by the conjugate, you've got to make sure that you're multiplying by a value of 1. So if you multiply by this fraction, that's equal to 1, it's not going to change the value of the entire fraction, but it's going to change its form. So make sure you have the same in the top and the bottom that you're multiplying by. When I go ahead and multiply this out, in the top I'm going to have 4 times, and if you want to put parentheses on this, if it helps you to remember to distribute. So 4 times 1 gives me 4, and then 4 times the square root of 5. And then down here, we're going to double distribute. 1 times 1 is 1. 1 times the square root of 5 is the square root of 5. Negative square root of 5 times 1 is minus the square root of 5. And then negative square root of 5 times positive square root of 5 is negative square root of 25. Now, if you notice here, the 4 plus 4 square roots of 5 in the numerator just stays the same, but notice these middle terms, these two are opposites. The whole purpose was to get rid of the square root in the denominator. To simplify your objective is to not have any more square roots left in the denominator. And notice these two, they're gone. They eliminate each other. Whereas in these other two, that square root of 25 is just equal to a 5, no more square roots. This fraction has the same value as our original, but has no square roots in the denominator. Now let's simplify. You've got 4 plus 4 square roots of 5 over negative 4. Now, it's important that you recognize when you see something like this, that number 1, you have a factor of 4 in every term, not just here and there, but in both terms in the numerator here, and also that negative. Now, the first thing is if you have a negative in the denominator, it is customary for us to multiply top and bottom by negative 1. So I'll do that first, even though I could do it all in one step. So I get negative 4 plus 4, minus 4 square roots of 4, or square roots of 5, excuse me. So minus 4 square roots of 5, all over positive 4. So it's customary to create a positive in the denominator. Now there's a common factor of 4 that I can factor out. So I have negative 1 minus the square root of 5 in the numerator, all over 4. And the 4's now reduce as a common factor. And so that gives me negative 1 minus the square root of 5 as my answer. This is the same equivalent to this one here. Now, it isn't often that you'll get rid of the entire fraction, but in this case, the fraction became just two separate terms. Now, on this one, what we'll do is we'll go ahead and multiply by, in this case, we'll do the conjugate of the denominator again, and you do it in the top and the bottom. So 10 minus 2 square roots of 7, and 10 minus 2 square roots of 7. And when you multiply that, you want to distribute to both of them, and you want to distribute both of these. So 9 times 10 is 90. 9 times negative 2 square roots of 7 is negative 18 square roots of 7. Negative square root of 7 times 10 is negative 10 square roots of 7. And then negative square root of 7 times negative 2 square roots of 7 is a positive 2 square roots of 49. All over, and in the denominator we double distribute, so you're going to have 100 minus 20 square roots of 7, and then plus 20 square roots of 7. And then lastly, when we multiply those two, we get minus 4 times the square root of 49. Now we need to do some simplifying for this, but as we do that, we're going to go ahead and combine like terms. So notice that in the numerator here, you're going to have 90, and then this is minus 18 minus 10 is minus 28 square roots of 7. And then up here, we're going to have plus 2 times 7, because that square root of 49 becomes a 7. And then in the bottom, we have 100, and then these two will reduce out. That's the whole purpose of using that difference of squares factoring pattern to our advantage, to get those middle terms to reduce out and no more radicals there. And then minus 4 times 7, because that's just square root of 49 is just 7. Now simplify further. We've got 90 minus 28 square roots of 7 plus 14 all over. Down here we're going to have 100 minus 28. Now remember, don't make some common mistakes here. I'm going to stop here before I simplify fully. Common mistakes are that people start looking, saying, hey, I can reduce out this 14 and this 28. Can't do that because they're not factors. They're being subtracted here and added there. Only factors can be reduced. These are not factors of the entire numerator. Another common mistake, I'm going to go back to the beginning and point it out here at this point. Another common mistake is that people do the conjugate of the numerator, and all that would do is that would get rid of the square roots in the numerator. Make sure you do the conjugate of the denominator and do it in the top and the bottom. That plus became a minus, and we do it both top and bottom. This value is equal to 1, so we don't change the value of the whole fraction. All right, let's simplify. 90 plus 14 gives me 104, minus 28 square roots of 7. And down the bottom, we've got 100 minus 28 should give us 72. Now we're looking for a common factor out of all of these. And I can, just like in this one, I was able to take out a 4. Well, here 4 is a common factor as well. Take out a 4, and this is going to be 4 times, in this case, that's going to be 26. Excuse me. 26. And then take a 4 out of this, and you have minus 7 square roots of 7. And down here, it's going to be 4 times, and this will be 18. That is the common factor. So the 4's cancel. And so that's our only common factor. So we're left with 26 minus 7 square roots of 7 all over 18. And that's our final answer. Now some of you might ask, why don't you separate it like we did with complex numbers? Well, with radicals we don't need to separate it, because complex numbers, you want a real part separated from the imaginary part. There is no imaginary part here. So you don't have to separate out the radicals in the numerator. All right, let's look at some monomial problems. So for this one, it's quite simple when you just have a square root in the denominator. You want to eliminate it. It's quite simple. You just multiply by that square root. So square root of 5 over square root of 5 will do the trick for us. So in the top we have 13 square roots of 5 all over 4 times the square root of 25. Then you get 13 square roots of 5 over 4 times 5 down here. So bring that square root of 25 out to be a 5. So you get 13 square roots of 5 all over 20. And there isn't anything that can reduce. I can't simplify a number in a radicand with the number outside. So make sure you're not confusing that you can reduce those there. All right, now the next one, I'm going to go ahead and simplify this one. Now notice there's a binomial in the numerator. You don't worry about that. You can have radicals in the numerator. It's the denominator I'm concerned about. Now I want to create a perfect cube here. And what I should recognize is that 36 is equal to 6 squared. So in order to get a cube, I need another 6. I need to multiply 36 by 6 to get 216, then it's a perfect cube. So what I multiply here, which is different than with the square root, is just simple. You multiply by the same radical that's down there. Here I'm going to multiply by the cube root of 6, because that will give me 6 cubed when I combine it with that 6 squared, and then I'll have a perfect cube. So here I'm going to have 2 times the cube root of 6 minus the cube root of 7 times 6, because they're both cube roots. You can multiply the radicands, is 42, all over the cube root of 216. And then so down here we have 2 cube roots of 6 minus the cube root of 42 all over 6, which is our final answer because we got rid of the radical in the denominator. There's a factor of 2 here, but there's no factor of 2 there to work with. Now, just a point on this, you might look at this and say, how is that any simpler than this? Remember, the overarching idea is when you're simplifying and you have radicals, you aren't allowed to leave radicals in the denominator. So that's what we've done, is eliminated the radical in the denominator. All right, let's move on to working with advanced cases when you have an even index. We're going to look at problems where you have an even index and talk about how you simplify that. Now, before we've talked about how to do it when it comes out nice and neat, but what if you have some leftover terms underneath, or sometimes you have odd terms that are in the problem. So these are going to have things left over in the radicand. We want to talk about how to properly use absolute value. That is kind of the idea. The big idea here is that when you have an even index in the radicand, so these guys here, even exponent in the radicand, so even index is what we're starting with, and then the exponents are even. These, you're going to always have to worry about the absolute value and what comes out, but you don't have to worry about the domain, because you can put any value in for r and t here, and it will, when you put it to an even exponent, it will come out to be a positive number, and we can't take the 6th root of a negative. Whereas down here, you're not allowed to put in a negative for x, because if you did, this would be a negative number under here, and then when you put it to the 4th root, you might end up having the root of a negative number. So let's start off with this one. When you have an even exponent in the radicand, you go ahead and separate it out. So you're going to make this the 6th root of 128, and this will be, when you work with the variables, use your rule of converting it to an exponent. So this will be r to the 20 over 6 and t to the 64 over 6 power. Now, 128, you gotta be able to work with that to find out, is there a 6th root in it? And there is a 6th root in it. 2 to the 6th power is 64. I'll just mark that off to the side. 2 to the 6th is equal to 64. So I'm gonna separate this and make it the 6th root of 64 times the 6th root of 2. So I usually use the numbers with the radical notation, but here's a clue for doing these. Put it into a mixed number like you did back in elementary school. I'm gonna make 20 over 6 equal to 3 and 2/6. Okay, I'm just not gonna reduce it because I still have a 6th root here. But notice that 6 goes into 20 3 times with 2 left over. And then for the t, 6 goes into 64 10 times with 4 left over. Now how that's helpful is the ones that are out of the fractions, that's how they come out of the radical. This becomes, if you look at this is a 2, 6th root of 2, and this is times r to the 3rd times the 6th root of r squared, because the 2/6 is not out of the radical. The t here will be 10 to the t to the 10th power times the 6th root of t to the 4th. Now you might ask again, why did we not reduce those down? Well, we gotta only reduce it if we can reduce in all the problem. So this one here, we're gonna go ahead and put 2 r to the 3rd, t to the 10th, the ones that came out, and then we're gonna have the 6th root left over of 6th root of what's left over underneath. There's a 2, there's an r squared, there's a t to the 4th. Notice those are all gonna be positive, so that's possible. Now, we gotta pay attention to our absolute value. Remember, our rule is when it comes out and there's an odd exponent on the outside, you've gotta put an absolute value on it, because this could be negative, and when you take the 6th root of something, you'll never get a negative value. So you gotta put an absolute value on it to ensure that it's a positive number. So that's our final answer. So the main points on there are, number 1, to go ahead and use your rule of converting the radical into an exponent on the variables, and when the variables come out, and if you have an odd result that comes out, put an absolute value on it. When it's even, you don't have to worry about the absolute value because it's always positive. Now, what happens if, in this case, if we have an odd exponent in the radicand? You are not allowed to put in a negative for x here, or a negative for y, because if you do, you would end up with a negative in here. One of them was negative and the other wasn't. So here we have to define that x has to be greater than or equal to 0, y has to be greater than or equal to 0 to even do the problem. What that does is that tells us when the answers come out, we don't have to worry about absolute value because we already know that they can't be a negative. So for this one, when we do it, I'm going to think about the 4th root of 625. I'm going to do x to the 13/4. Remember, make it into a fractional exponent. Y to the 27/4. The 4th root of 625, well, if you recall, 5 to the 4th power is equal to 625, so we get that to be just a 5, so that's a number that comes out. There's no numbers left underneath. And we're going to make these into mixed numbers. 4 goes into 13 3 times, and we're left with 1/4 left over. And then for the y, 4 goes into 27, goes in 6 times, with 3 left over for that. And now what I get then is 5x to the 3rd y to the 6th, the numbers, the part that are out of the fraction in those mixed numbers, they are out of the radical, and then we're left with the 4th root of x to the 1st, and then y to the 3rd, what's left under. Now I don't have to worry about any absolute value on this x to the 3rd because the original radicand had an odd exponent. That meant that this couldn't be negative in the first place, so you don't have to put it on. So that is advanced thinking on these problems, that if it's an even exponent in the radicand, you do have to put the absolute value on if it becomes an odd result. But if it starts out as an odd exponent, if you get an odd result out, you don't have to worry about the absolute value. So what we've done here is we've simplified our radical expressions. The first ones were when we had denominators and we wanted to eliminate the radical in the denominator. And then we did some advanced forms. We had an even index, the different cases of how to simplify those to get the values out of the radical, and then when you use an absolute value and when you don't use an absolute value.